So welcome back to the afternoon session. I am Marco Lippi from the University of Modena Reggio Emilia, where I am assistant professor, and I work in machine learning, in AI, and have been working in statistical relational AI during my PhD. And now I work with this instrument mostly in the application domains of natural language processing. I work also in bioinformatics. As you have seen, the goal of this lecture is to test what we have seen so far. So we will try to perform some experiments live with some of the tools that we have seen during this lecture. So in this sense, the lecture itself is going to be an experiment itself. Let's see how it succeeds. And I have put an updated version of the slides online on the page of the school, along with a zip file with some material, okay, that I will use during the lecture. Okay. As you have seen, I also sent an email a few days ago, and I'm going to use 3 different systems. Okay, so we will use Alchemy for Markov logic, we will use Problog, and we will use CP-Lint. Of course, there is a bunch of other languages, but I mean, there was some choice to pick up something. If you have not been able to install all the software on your laptop, or even if you do not have the laptop with you, do not worry, because you still will be able to play with the example, because I will focus a lot in the second part, mostly on the modeling of the problem. Okay, so of course we will also run the software and see what happens if you play with rules, with parameters, etc. But what I would like to see in the second part is really, if you are in front of a problem that you would like to deal with Star AI software frameworks, how would you build the model? Which information would you like to exploit, and how? Okay, so you can do that even on paper, in principle. Okay, then to translate it into a working example with the software, of course, is something which requires experience with the software itself, trial and error, and it's not something that you can do in 1 hour of a lecture. Okay, but anyhow, we will try and see. So, as I said, 3 softwares. So, first is Alchemy. Okay, this is the website, Alchemy CS Washington EDU. It has a nice website with a tutorial, a lot of examples with data set, models, a full list of publications related to Markov logic, so that's a good starting point. There are different versions. The original version 1.0 of Alchemy, but this is, as said, no longer under development. Version 2 is the one that we are going to use. And there is also Alchemy Lite, which is for what is called, I will briefly mention, tractable Markov logic. So it's a subset of Markov logic which is tractable. So it means that it allows to use more efficient algorithms, basically. There is also an implementation in Python, which is, there are more than one. I think the most used one is PracMLN, okay, for those of you who like Python. There is also, there used to be, I have to say, an online platform, but it's not available. So we will deal with that. So we cannot use directly the online demo on the browser as we can with Problog and with CP-Lint. So for Markov logic, I will use a command line, basically, you will see. Then we have ProBlog, which has a very nice website with really a lot of material, very nice introduction, many, many examples. And here you have, even in this case, as with Alchemy, a tutorial. And you have an editor, okay, which works. And here you can run inference, you can run learning, NP, and some other stuff. And finally, cplint also has a very nice website, cplint.eu. And again, you have an editor here where you can write your programs. Okay, you'll see how. Here you write your queries, and here you get the examples. Again, even in this case, as with ProBlog, you have plenty of examples, nice tutorial manual. So it's really another good place to start with. As for installing, just to quickly mention for those of you who haven't tried, or for those of you who tried but didn't succeed, Alchemy is C++, okay? So even version 2.0 is quite old, a few years old, I don't remember, but so it's not that straightforward to get it installed immediately. For example, on Mac, it doesn't with Clang. You have to install G++, okay? So in any case, if some of you is interested in to install it on its laptop, you can, keep in touch with me, and we'll figure it out, I hope. ProBlog is much, and also cplint are much more easy to install. ProBlog is really, if you have pip for installing Python packages, is one line. So pipe install ProBlog, and that's it. And also cplint has, maybe I can open it, the GitHub. There it is, from Fabrizio, with brief guide to installation. It requires SWI Prolog, which is a Prolog environment. Okay, this is actually the trickiest part to install again. So it's quite easy, but on Mac and I think also on Windows, even though I didn't try it, can be tricky to install it. So again, if you have problems, troubles, ask me or Fabrizio, of course. Once you have installed Swipe Prolog, cplint should work quite fine. Okay, so let's back to the slides are updated. So if you downloaded them a couple of days ago, please go and take the most recent version. Yeah, so the main idea is to start playing with these three frameworks: ProBlog and cplint, which means dealing with LPaths. It also works with ProBlog syntax. Have been covered mostly by the lectures of Professor De Raad and Professor Iguzzi. So we'll have in my lecture mainly, say, 4 parts. We'll have a first part, which is quite brief, in which I will recap what has been said in these days about using these tools from the point of view of applications. So a few things on some very practical but quite important problems. So for example, we deal with relational data, so how do we perform model validation, for example? Some of this stuff, this will be quite brief. Then I will talk about Markov logic networks, quite in detail because they have been mentioned in almost every lecture, but never being introduced properly. Okay, so since I am going to use them, there is need to at this moment. And that's the second part. Then we'll move really to the practical stuff. And I will have some examples which are in the zip file that you can download with already prepared files for Markov logic, for CP-Lint, for Problog, covering, I think there are in total 5 examples with some variants, so there's plenty to talk about it. And this I will do them. Okay, so I will present describe the solutions that I proposed for these exercises, and we'll talk about possible variants. And then the final part of the lecture, which I would like to be a little bit more interactive, will be with, say, exercises. So I will give you a problem with a tiny data set, okay? As I said at the beginning, I don't want you to, have your program running with those data, because it also requires some data processing. I don't want to arrive up to that, but I would like you to try to think how you would build your model in one of these languages, propose a solution, and then we discuss, okay? And then maybe I also propose a solution myself. Okay. Yeah, actually, here it's written that the demos on the browser have fewer features. This is more or less true. Actually, Problog and CP-Lint have almost all the features, I have to say, because the main limitation is that you are not using, it's a limited amount of memory, of course, but the features of the frameworks are almost all there. There is some work in progress things that are not yet ready, but maybe we will also talk about that soon. Practical, as you have seen, the online demo has much fewer features at the moment because it's not working. So back to what has been told you in these lectures up to now. We have to deal, when dealing with star AI applications, we have 3 main problems. Now you should know it's inference, parameter learning, and structure learning, which are strongly interrelated, okay? It could happen that in your problem you have to address one of them, you can address all of them jointly or not. It depends a lot on the applications and on the data that you have. Inference in statistical relational AI lies at the intersection of logical and probabilistic inference, okay? With logical inference, we mean that we want to infer the truth value of some logic facts given a collection of other facts that are known, okay, that are evidence, sometimes it has been said, and also, you know, some rules given by background knowledge of the domain, expert experience, and so on. In probabilistic inference, you are dealing with random variables, you want to infer the posterior distribution of an observed random variables given the observed ones. So logical inference is purely symbolic, okay? Probabilistic inference deals with uncertainty. When we do inference in star AI, we are in the middle, okay? Parameter learning, you have seen it quite some very interesting things this morning with Fabrizio's lecture. You have to specify parameters for rules, for logic rules in general. And these parameters can be probabilities, but can also be real weights, as you will see is with Markov logic. Okay, so this also is different from a model to another. And parameter learning wants to learn these parameters from the data that you observe. Okay, so you have say a template of a rule, but you do not know whether the rule is always true, how much it's true. You observe data and you want to get this information from the data. Okay, so that's parameter learning. Structured learning is probably the most challenging problem, I would say, and wants to directly learn the rules, so the structure of the model. And Fabrizio has introduced a lot of stuff about that this morning too. So sometimes you jointly learn the parameters and the rules, but there are also some, I would say, efficient methods that first learn the rules, as you would do in a typical pure ILP, pure logic world. Okay, maybe they are not that accurate rules, of course, because we are not in a pure logic world, we are in a probabilistic world. So you first learn a bunch of rules, and then you learn the parameters. Okay, but these three problems are clearly, strictly interrelated. So let's move to the task that we will in part cover during the lecture. So again, a lot of it has been said already. So we have, let's say, these are the three main tasks that you can imagine, but there is much more. You can classify entities in general. So you have objects in your world, and you want to classify something about these entities. Okay, so properties, categories, and so on. You want also sometimes do what is called entity resolution, which means you have entities in your world, but some of these entities are actually the same thing. Okay, the typical problem here is authorship resolution in a citation network. Okay, for example, my name in my papers can be Marco Lippi, can be n.lippi, can be Lippi m, and so on. It's always me. Okay, but if you have a huge database of papers, you cannot know in advance who is me. I also have a person with the same name, for example, in Rome. Okay, so who is me and who is him? Okay, so this is entity resolution. It's a typical example. You want to understand which entities correspond to the same object, real object. Okay. Link prediction also has been described. So you have entities and you have relations between the entities, and you want to predict them. Or sometimes you can associate and mix, to some extent, entity classification and link prediction if you want to predict properties of the links. Okay? So you do not want to predict whether a link is or is not there, because that might be given, but you want to predict the property of the link. Okay? So you have a traffic network, for example, and you want to predict whether between two nodes there is a congestion or not. This is something that we will see later on. It's interesting that for most of these applications, it would be interesting to perform what is called collective classifications, okay? Joint classification. So if you want to predict, for example, if, I don't know, users in a social network are spammers, okay? Of course, you can treat the examples as independent, but you may not want to. Okay, you may want to exploit the relations, and so to collectively predict whether a certain set of users is, each of them, spammer or not, okay, and so on. So as for entity classification, here are some examples. So user profiles in social networks is exactly what I'm talking about. You can have networks of bioinformatics domain. So you can have, for example, have genes or proteins, and you want to predict the function of a gene or a protein, okay, in a regulatory network. And this is predicting a category, a property of a node in this network, okay? Or congestion in transportation network can be predicted as a property of nodes or links according to how you model the problem. This is one of the examples that we'll see later on. It's interesting to see. You can, according to whether you model your domain, your transportation network in a way or another, you can predict congestions or nodes or in edges, basically. The same holds for peer-to-peer networks, internet networks, where you would like to predict maybe service requests or congestions in this kind of networks. Or fault diagnosis, for example, in sensor networks. You have sensors which are connected, and maybe faults propagate, okay? Hypertext categorization, so whether a certain page is of a certain topic or multiple topics. This is one of the examples that we will have, and so on. For all these kind of problems, which are the correct features? Well, the correct features is difficult to say, but which are the features that you can use, that you would like to use, that you should at least try to use? So, of course, if you have to predict a property of a node, clearly using attributes of that node is straightforward. You should use them, okay? But if you stop there, you do not exploit anything of the structure of your network, clearly. You use attributes of the neighborhood of each node, okay? So you want to predict whether a certain node is a social spammer, is a spammer on a social network, and so you use his or her attributes, but you also use the attributes of people related to him or her, okay? That's one thing that you can do. You can also use attribute coming from the whole graph structure. It could be useful. For example, this in bioinformatics particularly, it could be useful because the single properties of residues, for example, I think that it could be said that depend on the whole protein, in a sense. So that would be also an interesting set of features to use. Up to now, we are talking about attributes of the entity itself or other entities. And so we are still in a framework where, in principle, you could use traditional machine learning algorithms. You could use a standard neural network. You could use a kernel machine, as the ones that Paolo described yesterday. You could use decision tree, random forests, whatever, because you could still consider the examples as independent, okay? You want to predict whether, again, node A in this plot here is spammer or not. You build a set of features, okay, which includes the attributes of the node, the attributes of the neighbors, the attributes of the graph structure. So you really exploit the structure in the features. and only in the features, okay? And you use any kind of classifier that you want, okay? Are we doing relational learning? I don't know, maybe, at some extent, but we are not using something that collectively assigns a value to your nodes, okay? For example, A and B here in this network are connected by a link. So maybe you would like, depends clearly on the domain, but maybe you would like that they have the same label. Okay? If you treat them independently, there's no way to ensure this. Not even to hope that this situation has a higher probability. Okay? To some extent, maybe you could, but in principle, it's not the proper way to do that. Okay? What you would like to do is to jointly assign the class to A and B, so that A and B, being of the same class, has a higher probability that A is of one class and B of the other, or the other way around. Okay? That makes the difference. For link predictions, I'll be quick. It's similar. So you want to detect, predict, or infer whether there is a relation between entities. Okay, so this could be friendships in a social network, could be a recommendation, and we will see an example of that later, where nodes are of different types. So you can have customer node, product node, and there is a link between them. You want to predict maybe if a consumer is gonna like a product or rate it high or low, okay? And you want to consider his past experience of a customer. You want to consider the information of the product, and you would also like to see whether, for example, his friends have liked it, okay? So in this way, you take into account the relations also. And the same holds for transportation, internet, biological networks, as it has been more or less already said. Last example is something upon which I want to spend a couple of words, because again, it's an example we have later on. It's an argumentation mining, which is a natural language processing task. Okay? If some of you have ever heard about argumentation in general, it's the discipline which studies how humans debate, reason. Okay? So an argument is, you can think of it about a claim that you have, a statement that you make, okay? And it can be, for example, supported by some evidence, okay? And in this way, you can build graphs of arguments, because one claim can attack another claim, okay? Because they say one the opposite of the other, okay? And these are studied a lot in the domain of social sciences, politics, law, and argumentation mining is a very recent area that's very interesting. It's becoming very popular, which wants to use machine learning to extract these graph structures, okay, basically. So it's very challenging, because on the one hand, it deals with natural language processing, which is, I mean, becoming more and more effective with deep learning, but it also has a lot to do with reasoning. So it's very interesting. We'll see it later in more detail. So again, as for nodes, okay, even for links, you could predict the category of a link, or the presence of a link, according to some attributes of the nodes that are involved in a link. Okay, you can use attributes coming again from the whole structure of the graph. But again, if you stop there, you can use You can build a vector of features and use classic algorithms from machine learning. If you start taking into account relations at a much deeper level, then you should really use relational learning, okay? Clearly behind this, as is written here, is the concept, what is called homophily in the study of networks. So a link between individuals is typically highly correlated with the individuals being similar according to some similarity measure, which is not clearly always simple to define. So we know that examples are typically not independent this domain. The networks that we observe are very often dynamic. Okay, so they may change, they typically do, they change over time. Okay, one example is the one shown by Paolo yesterday about the Internet Movie Database, okay, which becomes different every time that, in principle, a new movie is inserted into the database, okay. We'll see that there are solutions to deal with dynamic networks, but this is something where I briefly want to spend some words because it's tricky to perform model, it's tricky. It's not straightforward to perform model validation on this kind of data, okay? So in dynamic networks, you may have nodes that change over time, so their property, their class changes over time. Okay, and links as well. Okay, so their properties change over time. For example, their category node is congestion now, but it's not maybe in 10 minutes. Okay, same for links. But the number of nodes, number of links can also change over time. Okay, so the structure of the network changes over time. So depending on the task that you have to deal with, at some point we may need to predict the evolution of the network. So you may use network at time t for training, okay, and the network at time t plus k for validation and testing, as described by Paolo yesterday for IMDb. He said that movies up to I don't know, year 2000 are the training set, and then you start adding some years and you have your test set, okay? When we have to deal with this kind of networks, you can have different scenarios. You can have a single static network, very big, huge network. You have a picture of that network at one single time, and that's all that you have. Okay. I've written here, this is an example, is recommendation, which of course can also be dynamic, okay, because you can have multiple, okay, photographs of the recommendation network, but consider that you have only one, okay, you have the data of a system for recommendation now, and that's it. So how can you perform model validation and training test split in this setting? Another possibility is that you have many small networks, like for molecules or proteins, or you can have a single evolving network. Now, it could be straightforward, but better to say that if you have a single static network, then the only thing that you can do is that you have split at some points. You have to cut some of the edges and to build a training set and the test set separate in order to train on data that are not seen, test on data that are not seen during training, okay? So how you split, that's a very good question. So there is no single answer. Of course, it depends on the domain. If there is some semantics upon which you can easily cut some of the edges rather than others. Of course, if you have many small networks, it's easier to say that some of these examples, for example, some molecules go into the training set and some others are the test set, and that's pretty easy, okay? Because all the networks are disjoint sets. Can be also disjoint communities in social networks. Or, of course, you can have an evolving network, as said, and then the picture of that network at time t becomes your training set, and at time t plus k is your test set. Okay, let's move to Markov logic, which, as I told you, is one of the software that we're going to use. So even though almost all the lectures have talked about that, it's time to see them in a little more detail. So we know that pure logic imposes constraints on the set of possible words, where with word I mean a truth value assigned to each variable, okay, to each atom predicate in your word. Markov logic, instead of hard constraints, has soft constraints, okay? So you have rules that, if are violated, make a word not impossible, but just less probable, okay? And formally, a Markov logic network is defined by a set of first-order logic formulae, okay? And a set of weights, where a weight is attached to each first-order logic formula, okay? So this is an example. You have the predicate friends, so X and Y are friends, and you know that X watched the movie M, okay? Then maybe also Y watched the movie M, okay? This is clearly not always true. There is a number attached to this formula, and the higher the weight, so the higher this number, the lower is the probability for a word violating that clause. So the higher is the weight, the stronger is that rule. You would like really that to be true, okay? Yeah, a word is sometimes, yeah, I may use also this phrasing, Herbrand interpretation is exactly a truth assignment, okay, to all the ground predicates. Now, be careful, because the syntax, even in the naming, can be misleading, because it's the other way around with respect to prologue, and thus also problog, but also cp-lint, because what is uppercase in one is lowercase in the other, and the other way around. So here, X and Y are lowercase, and they are variables, whereas in problog, variables are uppercase, okay? And the other way around, in prologue, you have lowercase constants, okay? Markov logic, you see in a minute, you have uppercase constant, okay? So it's exactly the opposite. So you have this list of rules, each with a weight, okay? And basically this can be seen as a template to instantiate a Markov network, okay? Using what? Using constants, okay? So given, this is the definition, given a finite set of unique and also possibly typed, and as we will see with alchemy, they are typed constants, a Markov logic network basically induces a Markov network. So a Markov network where you have a binary node for each predicate grounding, okay? And the value of this binary node is 0, 1 if the atom is false or true, respectively. Okay, and then you have an edge between two nodes which appear together in at least one formula. Okay, and then you have a feature for each formula grounding. Okay, in the Markov logic network, whose value is, again, 0, 1 if the formula is false or true, and whose weight is the weight of the formula, okay? So here is an example coming from the MLN that we have seen before. This is just a small portion of the Markov network. But with this, you can already see that, for example, I have this set of constants of two types. Type people, I have, for example, Alice, Bob, Carl, and David. And movie, I have Blade Runner, Forrest Gump, etc. And in this part of the Markov network, I have a node for each ground predicate. Okay, so I have substituted a constant to each variable. Okay, these are 4 of them. And I have a link in case that 2 of these predicates appear together in at least one ground formula. So, for example, if in the first clause here I substitute to X Alice and to Y Bob, okay, and to M one of the movies, I have an edge between Friends, Alice, Bob, and what movie Alice, Forrest Gump, for example, or The Matrix. Okay, here is the link. The same is for Bob. But of course, I do not have an edge between watched movie Alice, The Matrix, and Friends, Bob Carr, because there is no such a rule which together contains these two predicates. Okay? Now, if you go through the papers about Markov logic, they explain that they are quite general models that can have as special cases plenty of other models. There will be not much time to talk about this, but hidden Markov models, conditional random fields, logistic regression actually probably we'll see something later. But these in principle can be seen as particular cases of Markov logic. So what is the semantics now of an MLN? We have a probability distribution over all possible worlds, okay? So if X is the set of random variables of your model, okay, the MLN induces this probability distribution, so where the probability of world X, okay, so of the assignment lowercase x to the random variable set big X, follows this formula. So you have, this is proportional to you sum over all the formulas in the MLN. Okay, so F is the set of formulas in the MLN. Okay, and Ni is the number of groundings that are of that formula that are true in word X. Okay, so clearly the probability, and then there is an exponential, and everything is divided by what is a normalization factor. Z is the partition function. It's called the partition function, which is nothing else that the sum of the numerator over all the possible x's. okay? So that the probability lies between 0 and 1, okay? So basically, it is higher the probability of a world, all other things being equal, of a world where a weight is higher than lower, clearly, and also where the number of groundings is higher, fixing the weight, okay? These are the two crucial ingredients. So this is why there is a link with the Markov networks, where the probability distribution is a log linear model, which is basically identical. Okay, this one is the probability distribution of the Markov network, which is basically the same, where you have the weight, which is the weight of the formula, and the feature, which is basically the number of the groundings. We will mainly focus on a discriminative setting, okay? So the discriminative setting is the one in which you have something that some predicates that you always observe, which is evidence, indicated by X, and you have something that you observe only during training, but is what you want to predict at test time, and this is called query or non-evidence, okay? And is typically indicated with Y, okay? So for example, you would like to know whether Alice liked Blade Runner or Pulp Fiction, or Bob liked Runner or Matrix, given that you observe that some of these guys are friends and someone watched these movies, and during training you also have to observe these, okay? So that you can understand which are the links between the fact that someone watched the movies and the fact that they are friends and they like the movies, okay? In this case, there's nothing different. The only thing that changes is that you want to compute the conditional probability of Y given X, okay? And this time you have not the groundings on word X, but on the pair XY, okay? So X is fixed, is observed, and you want to compute the probability of the query given the evidence. So in the discriminative setting, one way of computing, of dealing with the inference, is to find what is called the most likely interpretation, the maximum a posteriori probability, the maximum a posteriori, world. So given the observed evidence, you would like to find the Y star, the assignment of truth values to the queries, which maximizes the conditional probability in principle, over all the possible Ys, okay? This is the most probable, okay, situation. Now, clearly, this is a very complex problem. The complexity is actually sharp P, so it's not an NP complete, but sharp P is also, as Christian and also Weishaupt said, are complex problems. They have to do with counting, so we have to use approximate algorithms. And one example, which is pretty intuitive, pretty simple, so I will briefly describe it, is MaxWorksAt, which is based on stochastic local search. Okay, so it tries to minimize the sum of unsatisfied clauses. Okay, or if you want the other way around, maximize the sum of satisfied clauses. Okay, so we want to have a word where satisfied clauses are those with higher weights. Okay, So it's a stochastic algorithm, as I wrote. This is more or less the pseudocode. So you have to fix in advance a number of maximum tries. Okay. You start with, in each try, you start with a random solution, so a random truth assignment, okay? And then you perform some flips, okay? You flip the value, change the value of one of your predicates, okay, ground predicates, okay? If in the initial random solution it is false, you flip it and it becomes true, okay? Now, what happens? Okay, if the sum of the weights of the clauses that are satisfied is already above a certain threshold that you accept, then, okay, you are done. This is your solution. Otherwise, you have to perform this flip, okay? So which is the atom that you flip? It works in this way. You pick a random unsatisfied clause, okay? Among the clauses which your word does not satisfy, you pick a clause, okay? With probability P, you flip a random variable in C. A random variable, so it's purely stochastic. You randomly choose the clause and you randomly choose also the atom in the clause. Otherwise, with probability 1 minus P, you flip the variable in C that maximizes, that brings you the greatest gain, basically, okay? Which maximizes the sum of weights of the satisfied clause. So it's necessary to also have a random component because it can be proven that the algorithm can get stuck in local minima. Okay, so randomness is a way to escape these local minima, okay? So it alternates greedy moves, which are the ones which attempts to look for the ground atom which brings you the greatest gain, and totally random moves, okay? What is the drawback of these is that you have to clearly build the whole ground network, okay? You have to build all the possible groundings of the predicates, which could be easily get huge, and we'll talk about that later also. Now, besides map inference, Markov logic also allows to compute the probability of it, that each atom is true. I will briefly say something, but not that much. I will talk about only one of these algorithms. The basic idea is that you have to sample, okay? In Markov logic, this is the way that it's dealt with. So you have different possible algorithms. I will briefly tell you something about MC-SAT, so it's Monte Carlo SAT, basically. You sample over basically satisfying assignments. Huh? But now there is also some interesting stuff about lifted inference also with Markov logic that's related to what Christian presented in the first lecture. So how this MC-SAT algorithm works? Again, you start with a random solution which satisfies all hard clauses, because there is something I didn't tell you yet. You can have also hard clauses in Markov logic. So they are clauses with infinite weight. So they cannot be broken. They must always be true. If all the weights are infinite, you have pure logic, pure first order logic. And you can with Alchemy if you want. So again, you have a parameter which is the number of samples, okay? And you loop over this number of samples, and at the beginning, you have to build a set M, which at the beginning is the empty set. And then, for all the clauses which are satisfied by the current solution, okay, for all the clauses that are satisfied, with a probability which depends on the weight of the clause, you add the clause to this set M. Okay, so in this way, in this loop here, you build a set M which is a subset of the clauses that are satisfied, okay, with the present solution. And then you randomly sample a solution satisfying M, okay? And this is how MCSAT works. And again, it requires the ground network. There is also what is called in alchemy a lazy variant, lazy SAT, it's called algorithm, which requires to ground only what is needed, basically, during the algorithm. Okay, so as long as you build the set M, so at the beginning you only have the clauses which are satisfied, so not necessarily you need all of them, and you incrementally build the ground network. Sometimes it works, sometimes you end up with building the whole network again. In my experience, if you perform the lazy version of the inference, okay, you start and you see, oh, it's really getting much less RAM, much less memory than the original. Then time passes and you see memory growing. Oh, and then you see that it reaches exactly the same amount of the non-lazy version. So it depends on the domain, on the problem, on the data you have. Let's briefly say how parameter learning and how structured learning work. I think that Sriram tomorrow morning will talk a little more about learning with Markov logic, so I will be fast on this. Basically, you want to learn the weights of the rules, so the W, okay, the WI attached to each rule, and so you can do gradient descent or something like that, and you compute the derivative with respect of the weight of the condition, again in the discriminative setting of the conditional probability, and this ends up to be, the gradient ends up to be the difference between the number of true groundings of the rule, which you observe in your training data, okay, and the expected number of true groundings according to the current weights, which means you have to run the inference. So inference is a subroutine of parameter learning here, okay? For each epoch of the parameter learning stochastic gradient descent algorithm, you have to run the inference. So that's quite costly, okay? And there are several methods for doing this. And again, I think that Sriram will talk about them tomorrow. Finally, how you perform structured learning. Again, there are many different alternatives. There have been variants that perform bottom-up closed learning, iterated local search. Actually, some methods which perform quite well with Markov logic basically do not perform Markov logic learning actually, because they perform ILP learning, for example, with Aleph, which is a famous ILP learner, or any other kind of ILP learner that you want to use, and you only learn the weights. So that's, I mean, like cheating, because you are not directly learning the rules within the framework, okay? So some remarks on expressivity here. So you can exploit first order logic. As I said, you can use infinite weights if you want to ensure hard constraints, so pure first order logic rules. You can use existential and universal quantifiers, okay? The existential quantifier is translated basically into a disjunction. So be careful to use that because the number of groundings can explode. If we have time, we'll show an example later. And of course, you can write rules where contradictions are allowed. Just a few words to say that there exists, as I show you at the beginning in the website, there exists a subset of Markov logic which is called tractable Markov logic, which is tractable, so it means that there are efficient algorithms to deal with, and basically it's a subset of first-order logic where relations have special shapes, subclasses, subpart, instance of, etc. They can exploit, for example, for inference probabilistic theorem proving. There is a paper on that, and you can find it on the Alchemy website. Basically, the key idea that's behind it is that you are capable of computing the partition function, this time in polynomial time, not in exponential time, both in time and space. But there is what's a software light version of Alchemy for tractable Markov logic. Okay, I want to do also a brief remark here on differences with respect to PROBLOG, with respect to LPAD. And the key difference is the fact that here, for the moment, we do not have seen probabilities, and we will never see probabilities attached to formulae. Okay, we have real valued numbers. Okay, so it's hard. This is a criticism over to Markov logic. It's hard to really interpret the absolute value of the number. Okay, so why is a rule weighted 1.2 instead of 3.4? And the relation between these weights is important, not just their absolute number. So while clear in PROBLOG and LPAD and other languages, you directly you see the probabilities, right? So it's much more elegant in this sense. Here we have the weights, and what is the weight actually is the log odds between a world where the formula is true and a world where the formula is false, other things being equal. If we let's try with an example to see whether it's clear. This is again the same formula that we had at the beginning. Okay, probability distribution. Now suppose that we have 4 rules. Okay, 1 grounding for each rule. Okay, so this n here can be most 1. Okay, and suppose you have 2 distinct MLNs where the only difference is that one of the rules has double weight. Okay, what happens of the probability distribution in the 2 cases? So you have the first Markov logic network where the probability is the exponential of W, supposing that grounding is 1, so they are all satisfied. You have W0 plus W1 plus W2 plus W3, okay, the 4 weights of the 4 formulae, okay. Then you have the second one where the only things that change, so other things being equal, okay, you have double the weights for W3. Okay, now if you compute the ratio between the two, sorry, here an X bit missing here, you have e to the W3, okay, the ratio. So the log of the ratio is the weight, okay. So that's the interpretation of the weight. It's not immediate, clearly. It's much less interpretable in the sense that dealing with probabilities, but that's the meaning of the weight. Okay, so going into more practical things and starting with then in a minute playing with our experiments. When you use Markov logic, when you use alchemy in particular, you have two different files that you need. One is called the MLN file, which is the template of your Markov logic networks, and one is the database file, which contains the facts, basically. Okay, so in the MLN, you have the definition of the predicates, which include the types, and the rules, possibly including the weights. So you can write the weights if you want to perform just inference, for example. You can write just the rules without the weights, and you have learn the weights. Okay. Then you have the DB file, which is the file of the facts, as I said, which includes ground predicates, both evidence and query during training, and only evidence during test. Okay, and here we have to make the distinction between open and closed word assumption. Okay, because what does it mean? Closed word assumption, and I don't know if all of you maybe are familiar with that, but it's better to say that again. Closed word assumption, if a predicate is closed word, it means that you only need to write down the true facts. No need to say that something is false. Okay? And this is what you do typically in the discriminative setting with evidence. Okay, in Markov logic. So if there is something that you observe and which is always given as a predicate, then it's typically closed word, and you only need to write the true things. Okay, so you have to, for example, assuming that friendship in the example shown before is evidence. Okay, you just have to say who is friends with who, but not who is not friends with who. Okay, you have just to say that Alice is friends with Bob and David, and not that Alice is not friends with Carl and Paul and blah 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 blah. Okay. Ground query predicates, so the one that you want to predict at test time, these are typically open word, and then you have to specify everything. So both true and false values. Okay. We'll see that. So let's start with one example. Are there any questions? Okay, that's the first example that you have in your folder, in the zip file that I sent you. It's a joining prediction problem. Okay, so you have a very tiny network where nodes have just one property, which is a color. Okay, and you have links, and it happens to be that the probability of link between two nodes depends on the colors of the nodes. Okay. So how can we model it with, for example, Markov logic? For this example, I have, if I remember well, all the models with Problog and also with CP-Link with Alpha. So MLN, there's one possible way is that you define 3 predicates for 3 colors. Okay, so yeah, red, blue, and green with one type, which is always node. There are only objects of one type, okay, nodes. And you have a predicate link between nodes, which is a binary relation between nodes, okay? This is the MLN file. So you first define the predicates with types, and then you write down rules, okay? So which are the possible rules is, well, first of all, you may, if you know that the link relation is undirected, okay, see, so it's not directional, you would like to ensure that the relation is symmetric, okay, so if link xy is true, if and only if link yx is true, okay, and if you put a dot here, that is the way in alchemy syntax to state that this is a hard rule, okay, so no need to learn the weight of this rule because you know that it is always true, okay, hard rule. Then you are writing down the combination of colors, okay, you can say that if x is red and also y is red, then there is a link, if they are both green, both blue, or the possible combination, okay, and that's one way to do that. How is the DB file built? So you have ground predicates with constants, okay? So uppercase, remember, in Markov logic have constants, so you may know that node N1 is red, node N2 is green, N3 is green, N4 is blue, and so on. And you know that N2 is linked to N3, N3 is linked to N2, okay? These are true facts. But for, as I told you, for the predicate that you want to predict, so link is the query predicate, since it is open world, you need to specify also the false predicates, okay? So you have to say that it is not true that N1 is linked to N1, to N2, and so on, okay? So the exclamative mark is the negation sign in alchemy, okay? So exclamation mark link N1, N1 means that the pair N1, N1 does not satisfy the link relation, okay? So before we for the learning for the open world predicates, yes. It runs the software also if you don't, but you do not end up with the results that you want. Because it's performing, since it's not assuming to know that this predicate here is false, since it's not assuming that, it's performing inference over it. So let's try that. So we also start seeing what, let me see, where is the stuff? I think it's on the desktop. Right. Okay. Okay, so for example, here you have different subfolders with the different models. Let's go to the version 1 for MLN, where you have your files. This is the Markov logic network file. Sorry, I have been too quick. I opened it with any text editor. I'm using the I because no reason to say why. Okay, so this is the MLN file. It's a plain text file, so you can edit it with any editor, which contains the predicates that I listed, partially listed before. Okay, and then you have the DB file, which is exactly what I was writing, and you have they are 100 in total, the link predicates, because I have 10 nodes, okay, in my tiny network, okay. So we can try, for example, to learn the weights of this MLN. Okay? How do we do that? We can use the learn weights binary file, which contains quite a huge number of options. Before we have a look at these, let's try to see if we first run an example. First example, where you need to specify what? First, the input MLN. So minus I, the MLN file. Then you need the training file, the training database, so minus T, the DB, okay? Then you need to specify an output file, which is minus O, where you would like to write the output MLN, okay? For example, I call it this way. And then you have to explicitly say which is the predicate which is not evidence, which is with the switch option and E. So what is not evidence? It's link. Okay, because all the rest is given, is evidence. Okay. So if you run it, starts doing things. Okay, takes a while. Even with this very tiny example, it takes a while. With the full parameters, clearly you have seen that there is a. Okay. Yeah, it also takes time because it's writing on standard. Okay, it's finished. So yeah, 37 seconds in total. This is the set of learned weights, but you do not see the corresponding formula, so we have to open the file, the out file that you chose to write. Okay, so if you open it, you see the rules with the corresponding weight. Okay, there is this strange format for which it's also useful in a sense, because basically each formula has two lines. One is a comment, because the double slash is a comment in Alchemy, and is the clause exactly as you wrote it, okay, so with the implication, while the other one is written in disjunctive normal form, okay, it only has not and or, okay. So this one here is a translation of not the antecedent or the consequent, okay? Not red or not red A1, A2, okay? It also substitutes the variables with A1, A2, A3, A4, okay? That's the way it does. So, are you convinced that these two rules are the same? Huh? Okay. So, these are the weights. So, just to try to understand whether this makes sense or not, the first thing that is, evident is that there are some which are positives and some that are negative. So first of all, what does negative sign means? It means that the rule is very unlikely to be true, okay, because the weight is negative, okay, and the other way around is very likely that its negation is true, okay. So what we observe here is that what is positive? It's positive that if the two nodes are green, they are linked, okay. The other positive example is one is red and the other is blue, they are linked, okay? And with exactly the same weight, even that X is blue and Y is red, so the other way around, okay, is linked. All the others are negatives. Huh? And in particular, there is also this prior. Can you read well also from the what? Okay. There is also a prior, okay, which says that the link predicate per se has a prior negative, okay, weight. So if you now are curious and want to see whether the weights that have been learned make sense or not, we go back to the database, okay? So remember that the only rules with a positive weight are both green and one is red and the other is blue. The only two rules with positive weight. So if we go back and look at the DB, which are the positive link ground predicates? They are 2, 3, and they are both green, 2, 10, and they are both green, and 3, 10, and they are both green. And they are the only possible green pairs, okay? What about red and blues? So the other positives are 7, 8, okay, which is a red-blue pair, 5, 4, which is another red-blue pair, and 1, 4, which is another red-blue pair, but these are not all the possible red-blue pairs. Because, for example, 9 is red and it's not involved in any other positive pair with no blue note. So that's why the green pair had a higher weight, because with red and blue pairs, yeah, sometimes it happens that them to be linked, but sometimes they are not. Okay. One thing that we can do with these is that we can perform now inference. Okay, we can use the network that we have learned. Okay, this one here. We need a test set. It should be here. Yeah, just 4 nodes. Okay, 2 are green, 1 is red, 1 is blue, and we want to see what this network is going to predict for that. So for this, we need the infer binary, which again has a very large number of options, but again, let's try to see whether we manage to run a first example without playing with the options. So in input, this time -e is the learned MLN, okay? So the one that came out of the learn weights program, okay? Then you need the input database with this time just to, confirm is not -t, but -e, okay? Which I think stands for evidence. And you give in the test files. Now remember, you do not have to put there the query predicates, okay? If you have them for measuring performance, you pull them apart and then you compare. And then you need to specify -r with that you want to write, okay, results, and it will write there the result of the inference. And then you have to specify which is the query predicate, which is link. Okay? Run it. It's done. Let's see what's in there in the results file. We have first of all, we have probabilities, okay, because the default algorithm for inference is MC-SAT, okay? I'll show you in a minute if we want to run map inference, how you do that. So this is the probability of each query ground atom given the evidence, okay? Now this is surprising in a sense because we didn't notice that before, but if you remember, 11 and 14 were green, okay? So they are predicted as with a probability that is greater than 0.5, 0.64, both symmetric pairs to be linked. What is also above 0.5, or anyhow significantly high, is the pair N11, N11, and N14, N14, which are close to 0.6. They are both green, huh? Even though the reflexivity property was not satisfied in the training set because there was no link. Let's have a look again. There is no link between N2 and N2. It's negative, okay? So it was not true, as I told you before, that all the green-green pairs are positive in the training set. When X and Y are the same, they are not. But there is no rule that specifies that. So it has learned a weight for pairs of green objects being linked, and so even one with itself gets a higher probability, okay? Then we have 12 and 13, which are red and blue, which have a higher probability with respect to others, but it's still quite low. Now, if we want to perform, then we do have the break. But if we want to perform, maybe it's better if I clear the screen again. If we want to perform map inference, we have to specify -a here. Okay. And now the file of the results is just 0 or 1. Okay, and this is the maximum a posteriori. It's a collected classification. The maximum truth assignment jointly done, okay, to maximize the probability of this assignment, okay? And you see that only the green pairs are true, red and blue pairs are not true, okay? Let's go back to the MLN that has been learned to understand why. Because there is a positive weight here, okay? So this weight is positive, but it's not enough to have a truth value of 1 because there is a prior which is strongly negative, okay? So this -1.2 is so strong that if you sum, okay, the contribution of the two weights, for the green, 1.53, it overcomes, okay, the sum is above 0, but with red and blue is only 0.76, so it's not enough, okay? So I think we can stop here. I want just to leave you with a question which you can think upon during the coffee break. So have we really done relational learning here? Okay, let's have a coffee break.